And in this video, we're going to look at what to do with the uncertainties for quantities that are squared or put up to some power. And we're also going to have a look at calibration uncertainties for digital measuring devices, which can often be quoted in a slightly odd way, and you just need to get a little practice using them. This will then lead us on to looking at how do we perform calculations with quantities that are measured in different units, and how do we combine the uncertainties of things that are in different units. So let's get on with example 2. As always, folks, if I'm going a little fast, because of course you're meant to be doing this a lot with your own measurements, just pause and allow yourself to catch up. So all of the measurements that I'm doing and all of the things that I'm doing, you should be doing with your own measurements from home as well. Make sure you really are going to collect those measurements, folks. It makes for a far more valuable and long-lasting learning experience. So in example 2, we are going to do the classic drop ball experiment. We're going to use the relationship S equals UT plus a half AT squared, okay? And we're going to use that relationship not to find the acceleration due to gravity, which is what we often use it for. We're actually going to use it just to measure the height of something, the height of drop. So we're going to drop something, so this is going to go to 0. Our acceleration is 9.8 meters per second squared. Even though we're dropping down, and that should really be a negative 9.8 meters per second squared, I'm just gonna, for this particular experiment, make the convention that downwards is positive, because the whole experiment is gonna be conducted in the downwards direction and just makes my life easier. So S is equal to a half AT squared, okay? We are going to measure the time of drop, and that will allow us to find the height of whatever you drop from. The reason I've chosen this one is, of course, t is squared, so we're going to see what happens and how you handle your measured quantity being squared and what that does to your overall uncertainty. So just to be absolutely clear, we are going to drop an object multiple times to the ground. We want to know what that is in meters, okay? And we are going to measure t. So we're going to set ourselves up a little data table, just like we did last time. We've only got a single quantity to measure, which is time in seconds. I'm a real fan of using just the symbols. If there's an official symbol for the thing you're measuring, just use the symbol in the data table. There's no need to use the word, okay? I'm going to be using my phone to measure the time. So let's see what precision my stop clock goes to. And so I'm going to be measuring my time to 2 decimal places. So that means my measuring device is 0.01 seconds. Never forget that unit. Okay. And I'd like you to pause me here, and I'd like you to complete this little data table just like we did for example 1. Try not to look back and get all the columns correct. See you in a moment. Okay, so I hope you've given room for your repeats, your mean, random uncertainty, and final uncertainty in T. So I should have put a delta C column right after that delta U there. I will put delta C underneath the table. It's much better just to have it part of your data table. So let's go away and get our measurements, and I'll see you in a few moments. So I'm going to make my measurements with the Firefox app because I do not want to have to start and stop my stopwatch with my finger, because I think that will add a huge amount of uncertainty to my measurement from my reaction time. Firefox is a completely free measurement app you can get on any Android or iPhone or your iPad or anything at all. Completely free, and it is fantastic for making those, all those kind of physics style measurements. I think the one that I'm going to use is the acoustic stopwatch. So I am going to make a sound when I drop the ball, and then the actual ball hitting the ground is going to stop the stop clock. You'll notice there's lots of different timers here. I'm just going to go for the one that I can use easiest and quickest, but I'm sure you could do other things. And if you wanted, you could take, for example, a slow motion video of the ball dropping to really get a very an accurate sense of the time that it takes. So do whatever you think is going to be fine for you. Lots and lots of different ways out there to get this time, but I really recommend Firefox as an app to have as a physicist. All right, I'll see you in a minute, folks, when we get our data. And random uncertainty, so my maximum was 89, my minimum is 303, that's over 5, to a single significant figure is 0.0. Now, my first significant figure here is a 1, 0.0172. In advanced higher, if your first sig fig is a 1, you can take the second one as well. So here my uncertainty is 17. Okay, and that puts the decimal places of my uncertainty in line with my mean. Okay, now as you can see, guys, I had a number of teething problems with my measuring, with my my technique here, and that's absolutely fine. And notice, guys, that I haven't tried to, oh, that should get crossed out. You notice I changed my measuring uncertainty because, of course, I changed my measuring device, my reading uncertainty, and then I kept getting these two kind of separate forms of measurement. I either got the 0.1s or the 0.3s. So I actually took a lot more repetitions than 5 to kind of establish which one was the problem. The 0.1s I found out was the sound of the ball, I think, slightly hitting the table just as it was dropping. I was lining my ball up with my table to drop from the same height every time, since it's the height we're trying to look for. And something was triggering the microphone there, so giving me too short a time. So there we go, there's my data. It's not pretty, but there we go. So let's do our calibration uncertainty. So we have to go and look up our calibration uncertainty. I doubt I've got a calibration uncertainty specifically for that Firefox. So we're going to have a look at the calibration uncertainty for this. Now, I couldn't actually find the actual calibration uncertainty for my Firefox app for that timer, and that is really, really common for a lot of measuring devices. Often things that have been in your school for a really, really long time, you just can't find the calibration uncertainty for them anymore, and you just go with quite a standard calibration one. So I'm going to use one that you see stated a lot. It might not necessarily apply very well to the one to our stopwatch here, but it really doesn't matter. And, you know, to be honest, as long as you make an effort to apply a calibration uncertainty, they just want to see you making an effort to incorporate all the issues that might be going on. Good scientific process. So it's really common for digital meters, particularly voltmeters and ammeters, but I'm sure it applies to stopwatches and things as well. They come with a calibration uncertainty that looks like this. Plus or minus 0.5% of reading plus 1 digit. You will see that quite a lot as the calibration uncertainty for a digital measuring device. So what on earth does that mean? Okay, what does that mean? Well, what we're going to do is it's 0.5% of our mean plus the smallest digit that can be, so basically plus your reading uncertainty. Okay, so for us, that is 0.5 over 100 times 0.331. So 0.5% of 0.331 plus 0.001. So we want to find that, and that is our calibration uncertainty. Okay, and that comes out as 3 times 10 to the minus 3 seconds. Okay, so to make that match up decimal places and those things, let's just check. 0.123 times 10 to the minus 3, 1, 2, 3 seconds. And actually, that matches in quite nicely. So that's 3 decimal places, 3 decimal places, 3 decimal places. So all of our uncertainties kind of come together to be relatively within the same order of magnitude. Now that's not absolutely necessary, but it does make you, it does kind of let you know that you're on the right track, that, you know, things, your uncertainties aren't way out there. So let's do our combining formula to get the total uncertainty in our time there. So that is the square root of our reading squared plus our calibration squared plus our random squared. And of course, guys, not everything will have a random uncertainty. You don't always repeat every single measurement that you take. If something's an independent variable, you won't necessarily repeat it. So then you would just cut off that section there. You just have delta R and delta C. That's absolutely fine. Okay. So for us here, this would be a good point in the video for you to pause and complete your own table: random uncertainties, calibration uncertainty, and combined total uncertainty in the time. 0.017 squared. And again, our random uncertainty is going to be king here. There it is. So our random uncertainty sticks, our total uncertainty sticks as 0.017. Actually, technically, I did not need to go through that process at all, because our random uncertainty is over 3 times bigger, both our reading uncertainty and our calibration. So I could have just simply stated it. Lovely. So we've got our time. So now we can go ahead and do our calculation. So when we do our calculations, guys, we do the calculation at first, completely ignoring the uncertainties, just do it as a standard. So we're going to find S. So S equals a half AT squared. That's a half times 9.8 times 0.331 squared. 0.5 times 9.8 times 0.331 squared. So they're saying my table is 0.54 meters high. That is obviously too small. So I'm measuring times that are too small. So luckily I didn't go with my 0.1 times, because that was way too small. Maybe I must have been dropping my ball before I made the sound. But anyway, it doesn't matter. It really doesn't matter. It's about getting data. So there we go. There's our S. So now we have to find the uncertainty in S. So to find the uncertainty in S, we have to look at our calculation and think, well, what uncertainties are contributing? Now in this calculation, the only thing that comes with an uncertainty that we measured, so the only uncertainty we're contributing here, is the uncertainty in T. And we're just taking 9.8 as an absolute kind of constant here. I know that it's rounded off. I know there is uncertainty associated with it, but we're not going to count that for this particular experiment. And you generally don't have to either. When you use things like that, accepted values. So that means that the uncertainty in S is the same as the uncertainty in T squared. Well, not quite. The percentage uncertainty in S is the same as the percentage uncertainty in T squared, because they're in different units. So we need to find the uncertainty in T squared to find the uncertainty in S. Now, for things that are at a power, so uncertainties for powers. If you have a value that you've calculated to a certain power, then the uncertainty in that value is the power multiplied by the percentage uncertainty in X. Okay, so to do overall, that's n multiplied by the absolute uncertainty over the value times 100. So let's look at that for ours. Delta t squared is equal to 2 times delta t over t times 100. So that is 2 times 0.017 over 0.331 times 100.
You could pause the video here, try and work ahead of me and see if you're on the right track. That would be a good way of finding out if these skills are really bedding in.
And that comes out as 10%. Okay, so making the uncertainty in the original t about 5%. And of course, I actually do want my uncertainties to be quite large here because I know my value is pretty wrong. So my uncertainty in delta t squared is 10%. Therefore, my uncertainty in delta in S is 10%. And so all I want to do now is turn that back into an absolute. So that's my S was 0.54, so that is 10 over, so delta S equals, that's percentage delta S, 10 over over 100 times 0.54 equals 0.05 seconds. Then my final value for S equals 0.54 plus or minus 0.05 altogether seconds. Let's double check our precision. So am I more precise than my raw data? No, I am not. So I don't have more sig figs than my raw data, so that's fine. Does my data, my process data decimal places match the decimal places of my final uncertainty? Yes, they do. If I didn't, I need to make this number, the result, match the uncertainty, not the other way around. Okay, so there we go. Uncertainty in S from the uncertainty in t squared. So folks, please go and apply this to your data for your height. Remember to rewind the video and watch back as many times as you need to, pause and apply this to your number. See you in the next one. Thanks folks.